everyone, so in this video I'm gonna be showing you how to go about solving a damped harmonic oscillator question. Okay, so we're given a problem like this and we can see that it is a damped harmonic oscillator because the amplitude is decreasing, and we are given that the mass is 3.4 kilograms. Now, the first question is to find the period of the harmonic oscillator. Now, looking at the figure that we have here, we can see that from here to there, which is a cosine wave, it's from 0.25 to 0.75. So from here to here, that's one cosine wave. And based on that figure, we can see that the period is going to be 0.75 minus 0.25, which is going to be 0.5. So the period is going to be 0.5. Okay, so that's 0.5 seconds approximately. Now the second question is to find the angular frequency, which is omega. Now, omega is going to be pretty straightforward. We can use that equation, which is t equals to 2 pi over omega. And solving for omega, we have 2 pi over t. Now, we have the period. We did find the period from here. So now we can plug that into this equation, which is going to give us 2 pi over 0.5, which is 12.6 radians per second. Now, that's the second question. Moving on. The third question is asking us to use the figure provided to solve for the damping parameter beta. So now we want to solve for beta. Now for this question, we know the equation for a damping harmonic oscillator, the equation of motion, which is this, which is x of t equals a times e to the minus beta t times the cosine of omega 1 t minus the phase change. Now this omega is not omega naught, which is the natural frequency. So this omega is the same as that one over here. Okay, so for this equation, this term is going to be 1, which, since this is 1, we are left with x of t equals a e to the minus beta t. Now that we have this equation, we can solve for beta. Have x equals a e to the minus beta t, dividing by a on both sides. This goes away. We have x over a equals e to the minus beta t. Once we take the natural logs of both sides of the equation, we have natural log of x over a equals natural log of e to the minus beta t, which this goes away, and we have natural log of x over a negative beta t, natural log of x over a, and then dividing by t on both sides. We have negative here and then beta here, and then all over, they're all gonna be over T. So now that's the equation we're gonna use to solve for beta. Now we can find these values from the plot that we have. Okay, so this is the figure that we have. And keep in mind that the damping parameter beta is what makes the amplitude decrease over time. So based on this plot, we can see that that A, which is the amplitude, is going to be approximately 2.9. So then this is going to be equal to 2.9 meters. Okay, so now for the position X, I usually use the second amplitude, which is this, the second wave, which is this. So looking at this, it's approximately 2.6, and from this, the highest amplitude to this amplitude right here, it's from 0.25 to 0.75, which is 0.5. So the time is going to be 0.5 seconds. Okay, so T is going to be 0.5, which is the same as the period, and X is going to be 2.6 meters. Now let's plug everything into our calculator and see what we get for beta. Now when I plug everything into the calculator, I get 0.22 okay 1/seconds. Now we're gonna solve for the natural frequency omega naught. We have this equation. Solving for omega naught, we have now we just have to plug the values we found in the previous steps. So this for beta and this for omega. Once I plug these values, I found that the natural frequency is 12.6 radians per second. Now we want to solve for the spring constant K. So we want to find what K is. We have this equation, which is the square root of K over M. Now, keep in mind that this omega is not this. It's not the natural frequency. This is omega 1, which is the resonant frequency. Now, solving for K, we have omega squared equals K over M, which gives us a value or an equation for K, which is omega squared times M. Now we have all of these values, and remember that M is it's given and it's equal to 3.4 kilograms, and omega squared is equal to 12.6 radians per second. Now plugging in these values into our calculator, we get 539 0.8 Newton per meters.